The Epsilon-Delta definition, also known as the formal definition of limits, provides a rigorous way to define what it means for a function's output to approach a specific value as the input approaches another point. Here's the gist. Intuitively, imagine a function like a machine taking numbers as input and producing output. As you feed the machine numbers closer and closer to a specific input value, does the output get closer and closer to a specific output value? Formally, epsilon represents the closeness you desire for the output to the limit value. It's like saying how close is close enough. Delta represents the corresponding closeness you need for the input to the input value. It's like saying how close to the input value does the input need to be. The definition says, for any epsilon greater than 0, there exists a delta greater than 0 such that for any input within delta of the input value, the output is within epsilon of the limit value. In simpler terms, no matter how close you want the output to be to the limit, by making the input close enough to the input value, you can guarantee that the output gets as close as desired. Let's prove the limit of 2x as x approaches 1 using the epsilon-delta definition. Given, let epsilon be any positive number, for example, 0.1. We need to find a delta such that for any x within delta of 1, the absolute value of 2x minus 2 is less than epsilon. We can see that the absolute value of 2x minus 2 is equal to 2 times the absolute value of x minus 1. Since we want this expression to be less than epsilon, we have 2 times the absolute value of x minus 1 is less than epsilon. To ensure this holds for any x within delta of 1, we can simply set delta equal to epsilon divided by 2. Why? Because then the absolute value of x minus 1 is less than delta implies the absolute value of x minus 1 is less than epsilon divided by 2, which automatically makes 2 times the absolute value of x minus 1 less than epsilon. With delta equal to epsilon divided by 2, for any x within delta of 1, we have the absolute value of x minus 1 is less than epsilon divided by 2. Therefore, the absolute value of 2x minus 2 is equal to 2 times the absolute value of x minus 1 is less than 2 times epsilon divided by 2, which simplifies to epsilon. We have shown that for any positive epsilon, there exists a delta equal to epsilon divided by 2, such that for any x within delta of 1, the absolute value of 2x minus 2 is less than epsilon. This proves that the limit of 2x as x approaches 1 is equal to 2 according to the epsilon-delta definition. This is just one example. Proving limits using this definition can be more involved for different functions. However, the core idea of relating the closeness of the input to the closeness of the output remains the same.